Hey, ladies and gentlemen. So, the formative you guys took on Wednesday, the first question, or all three of them actually, are talking about reactivity of elements. So, it's just based on the reactivity of metals or non-metals. So, the first one that we're looking at is our element list of metals. We got to figure out which one was the most reactive. So, the first thing we can do is look at our periodic table. And if we look at our periodic table, we'll see the valence electrons for all these different elements. All right. So the first thing we might notice is these three right here, 1, 2, and 3. They're all in that section that we haven't really talked about for valence electrons because they get more complicated. So technically, titanium has options, copper has options, zinc always has 2 valence electrons. For the most part, they're all going to be around 2 or 4 valence electrons. But the ones we do know are going to be lead, which is in column 14 on the periodic table, which we know has 4 valence electrons. And cesium, if we find it, it's in column 1 on the periodic table. So it has 1 valence electron. So if we look just based on reactivity of valence electrons, we know that cesium is the most reactive because it only has 1 valence electron. It also has somewhat to do with size because cesium is also one of the largest on there. It's not the only one that's large because we also have lead there, but cesium is one of the largest. But more importantly, cesium has 1 valence electron. That's going to make it the most reactive out of this group. All right. So make sure you're explaining why in this one, not just telling me which one is the most reactive. And number two is based on non-metals this time. So remember, our information changes. Remember, in metals, it's based on the smaller amount of valence electrons and the larger the atom. Now, in non-metals, it's the opposite. It's the most valence electrons, or the ones closest to 8, and the ones that are the smallest. Two things to remember, though, is that we don't care about our non-metals that are in the last column, column 18. And that's because those elements have 8 valence electrons. So things like neon and xenon have 8 valence electrons. And if they have 8, they're not going to share or give or take electrons from other elements, which is why things are reactive, which means that these guys aren't going to react. Right? They don't react at all. Right? They aren't going to mix with other things. Neon is always going to be by itself. Xenon is almost always by itself. There's only a couple instances where that ever changes. Nothing we'll ever see. The other ones that we want to think about is like boron and carbon and those ones in the middle where they're not even close to 8 because they have like 3 or 4 valence electrons. And with that few, they're trying to get all the way to 8, and having only 3 or 4 means it takes a lot of effort for them to get all the way up to 8. So they aren't going to react as often either. So now it's between nitrogen and fluorine. Nitrogen has 5 and fluorine has 7. Which 7 is the closest to 8. Fluorine is actually our most reactive nonmetal of any nonmetal, but because fluorine has 7, which is 1 away from 8 valence electrons, and is extremely small, it is the most reactive out of these elements, and it's actually the most reactive nonmetal in general because of how small it is. It's our third smallest or fourth smallest element behind hydrogen and helium and neon itself. So it's actually one of our smallest to begin with. Plus, it just has 7 valence electrons, so it wants to react. Last but not least, it's looking at based on the Bohr model and our knowledge of the elements. We know that silicon is very stable. It doesn't react with almost anything, right? And so we can determine that reactivity in general, elements can be very stable if they don't react, meaning You're not going to see them react with many things or at all, which is something why silicon's in our phones, that kind of thing. Now it asks, how does atomic radius affect the reactivity? So in general, how does the atomic radius of an element affect its reactivity? So we want to talk about two things. For metals, the larger the radius, the easier it is to take electrons, making it more reactive. And for nonmetals, the smaller, oh, sorry, I definitely just messed up. So hopefully we can see that, and we all make mistakes. All right. The easier it is to lose. Sorry, we're losing electrons with metals. So if you need to erase that, go back, cross it out, do whatever you need to do. Or it's easier to lose electrons for metals because metals have one or two and they want to get rid of those. Non-metals are smaller. So the smaller the radius, the easier it is to gain electrons, making it more reactive. Again, I apologize, but again, metals, they have smaller amounts of valence electrons, so they want to have larger atoms, and those larger atoms are going to have easier time losing that valence electron, making it more reactive, which is why the ones way down the bottom left, like francium and cesium and all those in that first column and all the way in the bottom, are going to be the most reactive. For nonmetals, the smaller the atom, because they have so many valence electrons, they're trying to pull more in. And those protons in the middle have an easier time pulling electrons from other elements if they're closer, meaning if the smaller the atom, the more reactive it's going to be because it has an easier time taking electrons, which is why fluorine, oxygen, chlorine are going to be more reactive than things like iodine because they're smaller. They can pull more electrons in a little bit easier. If you have any other questions, email me, let me know. I'm happy to answer any questions that you guys have. Otherwise, have a good rest of your week.